It's my pleasure to introduce Ross Stein, Temblor CEO. He is also a lecturer of geophysics at Stanford University, a former senior scientist at the U.S. Geological Survey, and a fellow of the American Geophysical Union and Geological Society of America. In 2015, Ross and Volkan Sevligan co-founded Temblor. They created a free mobile app and published web news articles. They created a free mobile app and published news articles to help the public understand their seismic risk and to help insurers manage their risk. Ross was the 2018 Thompson Distinguished International Lecturer of the Geological Society of America, a 2019 Centennial Lecturer of the American Geophysical Union, a 2020 Distinguished Lecturer of the Seismological Society of America, and a 2021 College of Fellows Distinguished Lecturer of the American Geophysical Union. Ross received the 2012 Gilbert White Natural Hazards Award from AGU. He gave a 2012 TEDx talk called Defeating Earthquakes, and he received the 2000 Eugene Shoemaker Distinguished Achievement Award from the USGS. And without further ado, here's Ross.
Thank you, Sarah. First, let me introduce and acknowledge my co-author. I'm fortunate to have been collaborating with Shinji Toda for so long that my now grown daughters call me Papa-san. Shinji is the principal architect of the Coulomb 3 software package, which has been downloaded 10,000 times and has been used and cited in 3,000 publications. Shinji himself is published in journals such as Science and Nature Geoscience many times. Now, Toda-san is a professor at Tohoku University and was formerly a professor at Kyoto University. Before that, he led the seismotectonics research group of the Geological Survey of Japan and began his academic career as an assistant professor of the Earthquake Research Institute of the University of Tokyo. Now, the only reason that Shinji isn't co-presenting here with me today is that there's no time slot that works for him in Sendai, myself in San Francisco, and for Temblor's London-based clients. But Shinji is the man behind the curtain, guiding the Gaijin. Now, the Noto-Hanto earthquake took 200 lives, wrought $25 billion of damage, only about $5 billion of which was covered by insurance. The quake unleashed a Pandora's box of ills: tsunami, landslides, liquefaction, fire following, coastal uplift. And the event sorely tested Japan's vaunted early warning systems, its building codes, and its hazard maps that are also central to its enviable seismic resilience. Now, most tantalizing, the quake nucleated in an intense seismic swarm that's been studied and monitored by the Japanese scientists for 3 long years. While it's hard to imagine that the earthquake was not triggered or nucleated as a result of the swarm, how the main shock was triggered is an enigma, and I will show you the clues, but I don't have the answers. And with that, let me begin the slides. Let me begin by showing you a map of the earthquakes and their sense of stress in Japan. So what you can see here is that the Pacific plate underneath the Pacific Ocean is being shoved underneath the landmass of the Japanese islands. And that occurs in subduction earthquakes, these red focal mechanisms, including, for example, the 2011 magnitude 9 earthquake. But there is also a zone, a broad diffuse zone of compression west of the Japan mainland in the Japan Sea. So this is a broad zone of deformation. It's not defined by any single fault, unlike the subduction zone that we have to the east, in which about 10 millimeters per year is being accommodated. And that in that diffuse zone is where the Noto-Hanto earthquake occurred. Now let's zoom in a little farther toward Noto-Hanto, and now you can see that this region has been the subject of a half a dozen magnitude 6 and larger earthquakes in the last 25 years. And because of Japan's rich seismic history, we know that an earthquake of the same size or larger occurred 400 years ago. So by any account, this is a very seismically active part of the country. Now, let me say something about earthquake early warning as it occurred here. This is an extremely difficult target because the area that was most strongly shaken is basically at ground zero. JMA, the Japan Meteorological Agency, issued the earthquake early warning 6 seconds after the main shock began. In other words, at that point, it hadn't become a 7.5 yet. It's still small. And so they called it for a magnitude 5.5, which wouldn't have predicted strong shaking. 33 seconds after the earthquake nucleated, they issued a second warning, now for a 6.6, and 57 seconds afterwards for a 7.4. What this means, unfortunately, is that nobody who was strongly shaken received advance notice. In contrast, in Sendai, 400 kilometers to the east where Shinji lives, he did receive a warning before the S waves, the strong shaking, arrived, and the same is true for the residents of Tokyo. So this was the hardest target for any kind of earthquake early warning system. Now, one of the most important and really alarming elements of this earthquake was the strength of shaking within about 30 or 40 kilometers of the epicenter itself. So you can see that for the standard USGS model, the shaking close to the earthquake is much higher, as much as an order of magnitude higher than expected. And this is a problem because, of course, all of the things that happen, such as landslides and tsunamis, they're all a function of the strength of shaking. And there are also 5 records above 100 centimeters per second in peak ground velocity. Now, if you're unfamiliar with these kind of measurements, we are accelerated downward at 100% G at all times. That's why when we stand on a bathroom scale, we have a weight. We're talking here about that same amount of acceleration, but sideways, where buildings have to resist that shear motion by their design. And that's very difficult to do once you get into the realm of 100 or 200% G. Building damage begins typically in a developed country like Japan at about 25% G and gets severe at 100% G. And this record is not alone. We just went through a year ago the Turkey earthquakes, where we also had records that exceeded our expectation for the strength of shaking near the fault. And I think together, these two earthquakes are telling us that when you have extremely well-recorded large earthquakes, you discover that your models are wanting and that we hadn't understood how much stronger the shaking can be close to the source. So this will be an important set of observation that will help us develop better ground motion models or revise the ones that we have. Now, how this strong shaking translates into all of these effects depends not just on this, but something about the topography and geology of the peninsula. So here is the topography, and you can see that the northern side of the coastline is the high topography, and there's low topography to the south. And if we do a cross-section, you can see the nature of that. Now, from Temblor's calculations or estimations, the Noto-Hanto earthquake has an inner event or repeat time of about 1,000 years, and the coastline was, on average, lifted up about 1 meter during this earthquake. What that means is, in terms of long-term rate of uplift, it's about 1 millimeter per year on the north, as you see there, and the peninsula just gets back tilted with time. And so that means that in the north, you have these very steep slopes in relatively young material, 5 to 20 million years old, that are susceptible to landslides. In the south, where you have a very, very gentle slope, you're susceptible to tsunami run-up because the water can get inland by only rising several meters. And in the incised valleys, in the high topography, that are filled with water-saturated sediments. This is what liquefies in liquefaction problems. So all of these ills are related to the nature of this long-term deformation of the peninsula. So let's take a look at some of those. So here's an example of landslides. This slide in the middle is buried a dozen homes. This is not vertically exaggerated. You can see how steep this terrain really is. And these slides have been extensively mapped by the Japanese authorities, and some of them are huge. Now, when it comes to liquefaction, it can't be mapped by satellite imagery. It's much more difficult to do so. But extensive ground surveys have already been conducted, and you can see here are just two examples of before and after images. And so these buildings have sunk by 1 or 2 meters. So no matter how much the building can resist the shear forces, the lateral shear forces that I spoke about, these buildings are a total loss because you simply cannot jack up a building that's dropped a meter. And so there's an enormous amount of damage, and it's not clear that that's been fully included in the loss estimates that I mentioned in the opening. And now when it comes to tsunami, as I mentioned, the very gentle slopes on the south east side of the peninsula are the problems. This entire western part of Toyama Bay was inundated by tsunamis, and in some places, the toll is enormous. So this is a tsunami height of almost 5 meters, and you can see that it's come inland about 400 meters and destroyed the harbor and this commercial and residential area. Now, what about the tsunami warning? It took about 12 minutes for the warning to be issued. Now, had this been a megathrust earthquake off the Japan Trench, 100 kilometers or more from shore, tsunamis move at about freeway speeds in the open ocean and are slower as they reach shore. So that would have been plenty of warning. But here, the tsunami source is so close that the first tsunami arrived long before the warning was issued. And the peak shaking only, or the peak tsunami only in some cases arrived after that warning. So extremely difficult to warn for a tsunami with this that has a source so close to shore. Now, let me show you where the Japanese succeeded extremely well. They had mapped these offshore faults in detail. And in fact, they had identified the fault that ruptured in this earthquake. And that's a huge achievement, particularly when it's offshore. And this was completed in 2010, 14 years before the earthquake. But what happened to this fault map? Well, you can see that it's been built into the Japanese government's model, which is called Herp, for Headquarters for Earthquake Research Promotion, and shows up as fault 43, the one that I just showed you. However, this fault was only used to assess the tsunami hazard. It was not used in the shaking forecast. I know that sounds inconceivable, so let me just show you what happened. So here are the offshore sources. There was detailed mapping for the onshore faults. The offshore faults are handled separately. There in the dark magenta color is the trench with the big subduction earthquakes. And you can see that there is a zone with moderate and low rank that corresponds to much of the contraction zone, the diffuse zone off the Japan Sea. But the region where this earthquake occurs had no sources, despite the fact that they were mapped. And despite the fact that Shinji and Owada-san argued after the 2007 Noto-Hanto earthquake, which was a 6.7, that the map needed to be remedied by the addition of these, inclusion of these active faults. So if one goes to the analysis tool of the Herp model, called JSHIS for the Japan Seismic Hazard Information System, one sees the peninsula, and it only has one source on it, the source of the 2007 Noto-Hanto earthquake. And since it had just occurred, the Japanese gave it a near zero probability of occurring again. So not only were most of these faults missing, but the near zero probability turned out to be dead wrong because this fault re-ruptured just 14 years later in this earthquake. So what does this mean? If you look at a map of Japan's hazard, you would be forgiven for thinking that the Noto Peninsula was among the most safe places to live in Japan, whereas that obviously was not the case. Now, I want to take a moment to contrast this with Temblor's stochastic event set, which is its simulated earthquake catalog. And as you can see, there are many large earthquakes expected in this region. And so this broad diffuse zone was captured. Now, in detail, if you look and see what were the earthquakes that were used in the creation of event set, it included about a dozen earthquakes from the seismic swarm at the tip of the peninsula. Event set is built from a blend of GPS-derived strain rate and the past 117 years of earthquakes. And these earthquakes were large enough and within the time period to be included. So one has to ask oneself, well, did event set get lucky, or is this actually part of its good design? I leave that to you, but I just want to say that the weakness in the national hazard map is unfortunate and could have been remedied. Now let's take a closer look at the fault that did rupture in this earthquake. These are the aftershocks in the first 2 weeks. And I think you can see from the red, green, blue character that on the Noto Peninsula, the fault dips or is inclined underneath the peninsula. But actually, the segment of the fault that is in Toyama Bay or in the Japan Sea dips the other direction. So these are called antithetical faults in the sense that one dips one way and one dips the other. And they're called en echelon faults because they're offset from each other here by about 15 kilometers. Now, people who make probabilistic hazard maps usually include some criteria for the possibility that one fault will jump onto another during a single rupture. But this 15-kilometer jump is so large that most would have excluded it from occurring, despite the fact that we saw that in the 2016 Kaikoura earthquake in New Zealand. So these rules that allow us to decide if a jump is likely or not also probably need rethinking as a result of this and other earthquakes. And so you can think of it as a compound rupture or a double rupture. And in that sense, it is not alone. We saw this in Denali, in 2 large earthquakes in Southern California, and in the Turkey earthquakes. And I think what this is telling us is gone are the days of simple planar ruptures like Northridge and Loma Prieta. As we have better data, we are seeing the true complexity of the faults. They're mangy, they interact, they're not continuous, and this is an element of the nature of the rupture. Now, another aspect of this fault is that it goes through this 40-degree bend here, and that has consequences for the amount of uplift that occurs. And if we look at measurements of the uplift from satellite radar interferometry, you can see this 4-meter uplift at the corner where this fault makes its bend. And we can model that process, and we get the same feature as shown here, with about 1 meter of uplift elsewhere and about 4 meters concentrated at the bend. And this has consequences. I want to show you aerial photographs from Kaiso Harbor. So here is the harbor in 2023. You can see the large harbor here and a smaller one here. And here's what it looked like after the earthquake. So the small harbor is completely beached. The large harbor is largely useless because the fishing fleet can't even enter it. the tsunami barriers are now high and dry, and these people for the first time have beachfront property. Let me just show you that one more time, because it's really staggering to see what 4 meters of sudden uplift have. The one benefit of this is that the tsunamis couldn't attack this area because it was uplifted as a result. But in every other respect, it's really a problem. And it's remarkable that it is greater uplift than occurred on Middleton Island in the 1964 Alaska shock, which was about 500 times larger. And I believe up until this earthquake had the highest coseismic uplift ever recorded. Now, lest you think that the features that I've been describing are unique to Japan and only Japan's problem, I just want to say Southern California has a half a dozen faults that meet this criteria, and I'm just showing them here. In other words, coastal, right lateral, reverse faults that, if they ruptured, could cause the same set of ills. And so Japan is not alone. And Southern California, of course, is only one of many areas in which we should think about the consequences of earthquakes of this type in coastal communities. So now let's turn our attention to the swarm, this utterly remarkable phenomena and hardly explicable. Here's what we know. The earthquake nucleated in the swarm, not the center, but as you can see, within the swarm. So there's that physical temporal association. The seismicity in this area was going along at a very, very low rate, and then suddenly, in about December 1st of 2020, took off, and its rate increased by a factor of 400. Why? There doesn't appear to be any external or internal reasons why this occurred. I've looked, and I don't see any global earthquakes larger than 6.7 that might have sent seismic waves through this area and somehow stimulated gas release or creep or fluids or anything like that. There's nothing which we sometimes see swarms turning on as a result of some global event. We don't see that here. A paper published yesterday in Earthquake Research Advances looked at a larger area and looked at the swarm seismicity. And I'm going to now, on their time series below, just remove the earthquakes that are below the level of uniform detection. And what I see here are the aftershocks to the magnitude 6.7 earthquake in 2007, which then decay to a low background rate. Then the swarm takes off. A 6.2 occurs in 2023, in May of 2023. But I don't see any continuous buildup. I don't see anything, any signals of something that we should have been able to read before. Now, in contrast, this time series by Judith Hubbard of Earthquake Insights is fascinating. So now we're looking at roughly the same box. First, you can see that the 1993 magnitude 6.6 earthquake, we're still getting aftershocks of this 30 years later. Here's the 2007 earthquake, which was not far from the swarm, and yet nothing happens. There's no turn on of swarm seismicity at the time of that 2007, which should have given it quite a whack, both dynamically when the waves pass through and permanently through static stress change. Okay, what about the Tohoku magnitude 9 earthquake, which is only about, 400 kilometers away? Well, nothing at the site of the swarm. There are some features that look like they do correspond, but certainly not here. And then there is something that happens in the end of 2011 that seems to correspond to the swarm and some areas to the north, but whatever that something is, I don't know. And then you see it starts to tick off in 2018, and as you saw on the time series plot previously, it really takes off in December of 2020, and then we have this 6.2 and its decaying aftershocks. Now, Yoshida and his colleagues have taken a closer look at the seismicity just in the swarm at the tip of the peninsula, and that's fascinating. They've divided it into 4 clusters of earthquakes, and they're showing you the time history. Now, this is depth in the y-axis of these events. And I think you can see that there is some upward migration in these cases. And we can kind of approximate that by some kind of curve. In the case of cluster S, that's the southernmost cluster, I don't really think you can fit it with any kind of curve. I've chosen to just say, well, we had activity at 16 kilometers, and then we had activity at 10 kilometers. And Yoshida argues that this suggests a diffusion process of fluids. This is the kind of curve you would get. But I think it's important to note 2 things. This upward migration is very minimal, 1 kilometer or 2. And it's been stable for the last 6 months. Nothing was changing unless I assume that this is error and not a real phenomena. But if it were, something happened at that time, but I don't think so. Now, Yoshida points out something else very intriguing over here in this southern cluster. There's a kind of a ring-like character of seismicity. Let me just toggle that so you see it again. And in general, one sees features like this associated with volcanic or magmatic processes, where there's either a magma plug, a magma body, or a caldera. And so he would argue that this is hinting at some kind of deep magma body, which presumably is releasing gases or fluids. These are volcanic sediments, but there's nothing active at the surface. So there's a hint, and Yoshida's view is that this is somehow a fluid diffusion process. Now, we don't just have seismic data, we also have deformation data. And that shows that the deformation, the uplift, swelling, basically an expanding of the peninsula, corresponds in time very closely to the seismicity. The seismicity took off here, and so does the uplift of about 2 centimeters, about 4.5 centimeters, and expansion of this east-west baseline by about 2 centimeters. The problem is you can model that rather easily, not just by a fluid process, but also by just slip on the thrust fault that we have now mapped. So just a little bit of slip on the thrust fault, and you would get the same kind of uplift and expansion that's been observed. So that doesn't give us one answer to the question, what is this caused by? Now, there's one more clue that Yoshida went back after the magnitude 6.2 Suza earthquake and looked for its relationship to the seismicity. And in this EE cross-section, you see something fascinating here, that at least some of the swarm seismicity really lies along a feature, which is probably the thrust fault that ruptured at the time of the 6.2. So this is the strongest evidence that the swarm and the main shocks are manifestations of the same process. Whatever is causing the swarm, be it creep or fluid migration, or fluids that migrate, lubricate the fault, and permit creep, it's also related to the occurrence of at least the 6.2. Okay, but what about the 7.5? It's too early to tell, because what we were just looking at was accurately relocated seismicity, and that needs to be done here, and to relocate the main shock and the immediate foreshocks that occurred in the few hours before the main shock. In cross-section here, it's not clear to me or Shinji that these really do lie along the same surface and not the same surface as the 2023 earthquake. So I'm sure Yoshida and his colleagues will be re-examining this to try to understand what their spatial relationship is, because that's such a crucial clue. Now, Takuya Nishimura has also analyzed the deformation and the seismicity, and he published last year a schematic view that argues that this is a fluid diffusion process with some kind of magmatic body at greater depth and earthquakes at first migrating upwards. and then into an opening crack, and then finally seeping into the thrust faults on which the big earthquakes occur. Well, this is an intriguing idea, but I don't see this northwestward migration of seismicity that's a central feature of this model. So I'm somewhat skeptical that this might be overinterpretation of the data that we now have. But this leaves a profound question unanswered. Is this Noto-Hanto swarm unique and unprecedented? And I think the answer is not quite, that there are similar cases. Famously, the 2009 L'Aquila earthquake was preceded by a swarm. In fact, the seismologists were at first convicted of manslaughter for not warning the population that this swarm would be precursory, which was preposterous, and they were ultimately exonerated. But the area in which L'Aquila occurred, the Abruzzi in the Apennines, there are many swarms, and most are not followed by earthquakes. You may not know that the Salton Trough near the southern tip of the San Andreas is an area of frequent seismic swarms every year or two. They only last a week, and thus far, fingers crossed, they have not been followed by a large earthquake. But I think it's fair to say that when we have the next one, our anxiety level will be even higher than it was for the last one. The EZ2000 swarm is probably the one that has greatest affinity to Noto-Hanto because it increased the seismicity rate by a factor of 1,000. That's twice as great as what happened here. But it only lasted 2 months, although it was followed by a number of big earthquakes. But in Izu, this is clearly a volcanic swarm associated with a giant dike emplacement. In other words, magma moving into a giant crack. And that isn't evident here. And finally, very recently, a migrating swarm preceded a magnitude 6.1 earthquake in China. And that might be another case that we should now look at as a lens to hold up against Noto-Hanto. So you've seen the tea leaves. They are hard to read. This is an important problem as yet unanswered. And kind of as a final issue that I think we have to address is, because this earthquake has an extremely productive aftershock sequence, it's definitely an overachiever. It's behaving more like a 7.8 than a 7.5. We need to concern ourselves with what could happen next. Where are we likely to get large aftershocks or potential progressive main shocks, as we have seen now several places around the world occurring? And to answer that question, Shinji and I refer to Coulomb stress transfer. And here's how it works for a little thrust fault, little square thrust fault that's blind or buried, doesn't come to the surface. And in these calculations, we're saying that in these butterfly wings, faults are brought closer to failure. And in these purple zones, which we call the stress shadow, seismicity rates should drop. This is not where we would expect aftershocks. Now, what are we actually talking about when we make these Coulomb stress calculations? Well, imagine our thrust fault, our 30-degree dipping thrust fault, and if you increase the shear stress in the direction the fault wants to slip and unclamp the fault, that's positive. If you were to do the reverse, subject it to stresses that would make it want to slip the other direction or clamp the fault or both, that puts it into the stress shadow. So that's what we're calculating here. We're not observing these stresses, we're simply calculating them. So one would like to know, okay, is this actually how the Earth behaves? And here's an earthquake that occurred in Southern California, the Northridge earthquake, of about the same size and character of that example. Here's its calculation with its butterfly wings and stress shadow zones. And here is the seismicity rate change comparing the 6 months after the earthquake to the 6 months before. And I think you can see they're correlated. They're not perfectly correlated. And for various reasons, it's much harder to measure the seismicity rate drops than it is to measure the rate increases. But I think you can see that there is something to this, and many other studies have shown the same thing. And if we go back to that Northridge-like case and compare it to a more Noto-Hanto-like case with much larger rupture, you see that the larger rupture is relatively less efficient at transferring stress along strike. And it has a much bigger, more profound stress shadow, which is good news for those living near Noto-Hanto. Okay, so how does that compare to calculations for this earthquake itself? So here we're using the initial USGS finite fault model, which is still under redevelopment. Most of the slip is occurring here. How this differs from what I showed you before is the slip isn't uniform, it's glumpy. There's certain places where it's higher and certain places it's higher here and lower elsewhere. But you can see the stress trigger zones beyond the end, and you can see the expected shadow zone in this model. But what's really oversimplified here is the faults on which stress is received. We're assuming that all the faults were just parallel to this one, like a set of Venetian blinds. And you can even see from the map faults, that's not the case. So we can do a little better by having probably a more realistic set of faults that slipped and using simplified versions of the mapped faults as the receivers of stress. When you do that, you see that these faults have been brought closer to failure to the southwest of the earthquake, as well as the faults near Sato Island to the north, whereas in Toyama Bay, in that stress shadow zone, fortunately, those faults would appear to be brought farther from failure and are now less likely to rupture. Now, we can make one more step here, which is rather than using a kind of idealized version of map faults, we use focal mechanisms as the receivers of stress, these little beach balls. Now you might say, well, why do that? Well, it's because we actually have an earthquake there on that plane. So we know that there is a fault, even if it's a little one. And so that probably gives us the most realistic way to understand the receivers of stress. And we combine this with the idea that a stress increase, what it does is increase, it amplifies the background seismicity rays, and a stress decrease suppresses the background rate. So that's calculated into this version of things, which is called rate state Coulomb. And then this is the answer that we get. It still has stress trigger zones and shadows in roughly the same places. You can see where we would expect fewer earthquakes, but now this starts to show up here on land. And these features, big stress triggers beyond either end, are still there. So this is our forecast for the seismicity rate change in the month starting tomorrow. And so you can see that the chances of contagion are real here. And we should be alert to the fact or to the possibility of subsequent large earthquakes. I'd like to close with the thought that this earthquake manages to combine all of our fears for the destructive power of these events. But it also carries the seeds of hope that we might learn how to assess whether a swarm, and they occur frequently around the world, is precursory to a large earthquake. That's the task at hand, and it's an exciting and important target of research. Thank you.